All right, so the lesson from your textbooks in Pre-Calculus 30, 7.2, page 346. We're going to talk today about transformations of exponential functions. In 7.1, you were introduced to the exponential function, which looks like this, y equals c to the power of x. If we go back to our notes here, you wrote down that an exponential function is where the x, or the variable, is in the exponent position. Okay, we built a little table of values and how to place points on this graph and how this graph is formed. Obviously, if you have a different c value, the shape of the graph is going to be a little bit different, and that's what 7.1 was all about, exploring how the c values affect the graph. What today's lesson is about is how transformations affect the graph. So we've talked about transformations before in the early chapters of this course, and we're going to do the same thing here with an exponential function. So this is the base exponential function where you have c as some constant that's taken to the power of x. So I want you to, this is in your textbook. You don't have to write these notes down. You can if you want, but no, it's up to you. But what we're dealing with here today is sketching the graph of an exponential function in the form of, and here is the exponential function with the parameters built into it. Okay, so I'll go over these one at a time, but from this base graph, we have a constant to a power. We're going to add a value of a, okay, as another number or a coefficient in front here. Okay, so that's a. We also have b. So b is another number that would be multiplied by the x. b is 1 in our base function, but if b is something different, we're going to explore how that changes things. Then we have h, and so this should start to look familiar with other forms of functions. Okay, what does this h do? We're going to find out about that. And then we have k here, and k is not in the exponent position. K is a constant that is added to the end here, and it could be positive or negative. So that's what this format looks like. And if you remember just a basic, y equals f of x, remember we put the a in front and that did something, and the b in front of the x and that did something, and so on, h and k. So we'll study this kind of one at a time. Okay, c, the important thing here is c is positive, right? C is greater than 0, because we talked last lesson about if c itself was negative, we wouldn't have that exponential shaped graph, right? We wouldn't have anything that looks like this. Instead, the points would be like popping back and forth, positive, negative, and they wouldn't form a graph at all if c was negative. So that's why c has to be greater than 0 under our consideration, or else it's not an exponential function. Okay, it's not an exponential graph that we're studying. All right, so as in other transformations, we're going to look at a and b first. So you start from the left to right, you do the a, and then you do the b. Okay, you apply those transformations first, and then you can do the h and then the k. And that's because a and b, just like they were in the past, are stretches. Vertical stretch, b represents a horizontal stretch. H still represents a translation or a movement left or right, and then K is a movement up or down. So all of these are the same as they've been in the past. And what we're going to do is we're going to look at one parameter at a time. Okay. So this is in the key ideas at the end of your section. We're going to go over them one at a time, and we're going to take a look at A first. Okay. In other transformations, A is a vertical stretch about the x-axis, okay, by a factor of absolute value of A. So A is a vertical stretch just like it was before. If A is negative, then it's a reflection about the x-axis, okay? So we're going to just explore this and confirm this to make sure that it's true. So we're just going to zip down, and I have this piece of your textbook on the screen here. And so on your calculator, why don't you go ahead and do this here? Y equals 3 to the power of x. We try that, and I have a few things up there already, but let's do 3 because they have 3 as the base function. Okay, so I'm going to clear these others. And the window, in case you're interested, this is what I did for the window. Just so we could see this a little more clearly. X min negative 2, X max 10. And then Y min was negative 2, and because I'm using the 3 now, I think I'll maybe up this to 30. Okay, so negative 2 to 10 and negative 2 to 30. And that, your graph then should look something like that. Okay? Everybody got that? So this is the Y equals 3 to the power of X. Okay, and so here it is roughly on the graph here like this. What is the y-intercept for this graph? Yes, it's 1. That's right. If we're just looking at the c value to the power of x with no other numbers, and specifically we're going to find out about this number here, a, okay, it's always y equals 1, just for your base function. And here you have y equals 1 as an intercept. Okay, so the other graph that they show here is y equals 4 times 3 to the power of x. So make sure that you don't write it like this, 4 times 3 to the power of x. That's not the a value. This is part of the c value here, right? So you have to be careful to put your bracket on the right side there. Okay? So why don't you try that, put that in your calculator and see what that does. So 4 bracket, 3 bracket to the power of x. That's x. Yeah, that should be x. Yeah, it does look like 12. Okay. Thank you. Thank you. So here's your graph. Y equals 4 times 3 to the power of x. Okay, and these are what the two graphs look like there. Okay, so the thing you want to make sure that you're not getting confused with here is that this is not a translation to the left. And this is the tricky part. Sometimes you can't really tell just by looking at the graphs whether this has moved left or this has stretched up. And that's the same problem that we ran into in previous chapters, right? The whole vertical stretch and the horizontal stretch sometimes are really difficult to actually see. So if we come back to this graph here, okay, the 4 is a vertical stretch, and it moves everything up by a factor of 4. So where y equals 1 on the original graph, y now equals 1 times 4. See that? Okay. So where, and this is going to get tricky. Let's say, so this one, excuse me, this right here is about 1/3. Okay, that's about 1/3. So 1/3 times 4 is 4/3. Okay, and everything should line up. Now, unfortunately, we don't have much more of a graph here, but if we go back to our graphing calculator, we're going to be able to see something. So if you go second function, trace, and you just hit enter for value there, and you have x equals, well, let's say x equals 0, right? What do you have? Well, you have 1 for the original function y equals 3 to the power of x. If you use your cursor to go to the next function, and with the same x value, you see that it's 4. Okay? And so that 4 causes a vertical shift. If we did another value, like 2, then for this graph, okay, 3 to the power of 2 is 9. Okay? And if we just used our up arrow to go to the next graph, okay, y is 36. Does that make sense? Well, 3 to the power of 2 is 9 times 4 is 36. Okay? So everything should line up. Now this is not on the screen, but it's going to be up here, right? Directly in line. Okay? So vertical. if you tested points this way, right, you would probably find that, hey, that doesn't actually line up, so it's a vertical translation. Questions? Okay, the other part of it is then, if A is negative, then that's a reflection about the x-axis. Okay, so if we have y equals negative 2 times 3 to the x, well, here's 3 to the x. A 2 would cause this point to go up to 2, and a negative causes the y value of that point to be negative. So there you have your y equals negative 2. There's an intercept. If x was 1, right, 3 to the power of 1 is 3 times negative 2 is negative 6 down here. So there's negative 6. Okay, everybody got that? So if you want in your calculator just to confirm this, we're going to have to change our window just slightly. We're going to have to give ourselves a little bit more room at the bottom, so maybe a negative 15. And then you go to y equals, and you can do negative 2 bracket 3 to the power of x. So there's your original graph. There's times 4, moved up. And then there's the other graph coming down there. Okay? Reflection. So you know what A does then? We're good? Okay. So here's what happens to B. Okay? Erase this for now. So B, so recall we're doing y equals, we've got A, and we've got some constant. Now we're talking about this number that would be multiplied by x there. And B indicates some kind of horizontal stretch, so just the same as before, right? The horizontal stretch is always by a factor of 1 over b. Get that line right. By 1 over b. Okay? So in this case, they're doing a base function of 2 to the power of x, and they've added a b value of 3. Okay? Okay, so if we compare these on our graphing calculator, 2 to the power of x and 2 to the power of 3x, okay, that's going to be the same as this one here, then what should happen is there should be a horizontal stretch of 1 over b, or 1/3. See that? 1 over b. So the x value, so let's graph that and see. Okay, so here's our y equals 2 to the power of x, and here is our 2 to the power of 3x. Okay. So little bit more difficult to see, these factors over here, the y value and the y value comparing the x values. But if we go back to this one here, so on this graph, okay, let's pick out some points like this one. On the base graph, right, this is y equals 2, it's x equals 1. Okay? I just put in this one and this one into the graph. Okay. But if you look at this, if x equals 1 here on this base graph, if you have a b value of 3, the x value should be compressed to 1/3 of its original. So 1 divided by 3 should be 1/3, and that's what we have here. See, that is now 1 over 3. So everything is compressed in the horizontal direction. So over here, what's this one? This is 2, right? See, a y value of 2. And so 2 over 3 should be, 2/3. So there you go. That's 2/3 right there. 1/3, there's 2/3. So everything should come over by a factor. Now, obviously 0 divided by 3 is still 0. That's why it's the same value. Okay? This one's, I don't think they do a real good job of drawing it here because it doesn't really look very good, but if this